Section: Introduction. In this section, we introduce the concept of context attribution and define how we can evaluate methods for it. We begin by looking at how to attribute an entire generated response, and we will later discuss how to attribute specific statements. To set the stage, we consider using a language model to create a response based on a given context. We define our language model as one that predicts the next word based on the words that came before it. We denote the probability of the next word as being dependent on the previous words. We also define our context as a series of tokens and our query as another series of tokens. The response we generate consists of tokens that we sample from the model, based on both the context and the query. Specifically, we express the probability of generating the entire response as the product of the probabilities of each individual token, given the context and the query. Section Summary. In this section, we introduce the concept of context attribution, which allows us to identify the specific parts of a context that influence a language model's generated responses. We also outline our contributions, including improving statement verification, enhancing response quality by refining context, and detecting context poisoning attacks. Section: Context Attribution. In this section, we focus on context attribution, which aims to link a generated response back to specific parts of the context, referred to as sources. These sources can be any subset of tokens from the context, such as documents, paragraphs, sentences, or even individual words. For our work, we primarily consider sentences as sources and utilize a standard sentence tokenizer to break the context into these sources. A context attribution method, which we denote as tau, takes a list of sources and assigns a score to each, indicating its importance in generating the response. We define this process formally. Given a context with sources, a query, a language model, and a generated response, the method tau assigns scores to each source to reflect their significance in producing the response. Next, we explore what these context attribution scores actually represent. We distinguish between two types of attribution: contributive and corroborative. Contributive attribution identifies sources that lead to the generation of a statement, while corroborative attribution finds sources that support or imply a statement. We focus on contributive context attributions, as they present unique applications. For instance, if a model misinterprets a fact and generates an incorrect statement, a contributive method can pinpoint the misinterpretation, allowing us to verify or correct the model's output. To evaluate the quality of our contributive context attribution method, we propose two metrics. The first, the top k-log probability drop, assesses how the probability of generating the original response changes when we exclude the highest scoring sources. The second metric, the linear data modeling score, LDS, measures how well the attribution scores predict the impact of excluding a random subset of sources. We define a context ablation as a modification that removes certain sources by eliminating their corresponding tokens. The top k-log probability drop is calculated by observing the change in probability when we exclude the top k sources identified by our method. This metric helps us compare different context attribution methods based on the importance of the sources they identify. For a more detailed evaluation, we also analyze whether the attribution scores can accurately rank the effects of removing different sets of sources. We sample various ablation vectors, compute the summed scores of the included sources, and measure the correlation between these predicted effects and the actual probabilities. This correlation, known as the linear data modeling score, LDS, allows us to assess the effectiveness of our context attribution method. Section Summary. In this section, we explore context attribution, which aims to identify the importance of specific parts of the context, sources, in generating a response, primarily focusing on sentences as sources. We differentiate between contributive and corroborative attributions, emphasizing that our work studies contributive attributions, which help identify misinterpretations by the model, and we introduce metrics to evaluate the quality of these attributions based on their impact on response generation. Section: Attributing selected statements from the response. In this section, we focus on attributing specific statements from a generated response rather than the entire response. We define a statement as any continuous selection of tokens from the response. To attribute specific statements, we introduce a context attribution method that takes additional arguments to specify the start and end of the statement we want to analyze. Instead of looking at the probability of the whole response, we now consider the probability of generating just the selected statement. We previously established that a context attribution method is effective if it can predict how including or excluding certain sources affects the original response's probability. Our goal with CONTEXTCITE is to find a simple model that can approximate this relationship. If we can achieve this, we can better understand how different sources impact the response's probability. Our approach involves several steps. First, we sample a set of ablation vectors and compute their corresponding probabilities. Next, we train a surrogate model that approximates the original function based on these pairs. We then attribute the behavior of this surrogate model to individual sources. For the surrogate model to be useful, it needs to accurately model the original function, be efficient to compute, and provide scores that attribute its outputs to individual sources. We found several effective design choices. 1. We predict logit-scaled probabilities instead of direct probabilities to avoid issues with bounded values. 2. We use a linear surrogate model, which, despite its simplicity, often provides faithful representations. Each weight in this model indicates the effect of removing a source. 3. We also learned a sparse linear surrogate model, as we observed that only a few sources typically explain a generated statement well. We induce sparsity using lasso, which helps maintain a faithful model even with fewer ablations. Finally, we sample ablation vectors uniformly from the possible subsets of context sources to create our training dataset. We summarize our method, CONTEXTCITE, and provide examples of its attributions.